Section 3 goes in the opposite direction. Instead of taking a z-score and finding a probability, we want to have a probability and find the accompanying z-score. And then we could then turn around for a non-standard normal distribution and find out what x-score went with that. So basic idea is when we want to find a z-score from a probability, we identify the region under the curve that corresponds to a given probability. If the area is not a cumulative region to the left, work instead with a known region that is from the left. Locate the closest probability in Table 4 and identify the corresponding z-score. In the previous section, we asked what percentage of men has a height less than 80 inches, the standard door height. We got z equals, and there's our 3.93, which corresponded to the 0.999 if you wanted just the 4 decimal places. Suppose the question is, how high should the door be so that 95% of men can fit through the door? First, find the z-score that matches 0.9500 from the table. So, if we go look at our table, and of course, remember, it's usually split into 2 pages. The positive scores on one page, the negative scores on the other. Areas less than 0.5 will be on the negative side. Areas greater than 0.5 will be on the positive side. We want 0.95, and so if we look right here, we have 0.9495, 0, and here we have 0.9505. And so generally speaking, when you get a situation to the 4 decimal places, I know this one gives you a 5th one, but let's just say to 4 decimal places, if you fall closer to 1, then you're going to pick that z-score. If you fall halfway in between, and so 0.9495 and 0.9505, we end up being 0.95, exactly halfway between those two, and so we would end up with 1.6, and then this one's 4, that one's 5, and so we're going to end up with 1.645 as our z-score. So again, we look in the table for the area that matches the probability we're interested in, and then we go to the side and the top to find the z-score. Generally, we just pick the z-score that's closest, but occasionally it seems to fall pretty close to 4 decimal places, halfway in between. If that's true, we add an extra 5 at the end. Otherwise, we'll just have 2 decimal places for our z-scores. Now, once I have that z-score, I can use this equation, which is our z-score equation, but it's been rearranged to solve for x instead of solve for z. So it looks like this. We plug in the z-score, we plug in the standard deviation and the mean. So for the men, 1.645, 2.8 was the standard deviation, the mean was 69. We end up with 73.6 inches. So about 74 inches would let in 95% of all men. 74, that's only 6'2", whereas the 80 inches that we had before let in beyond 99.99% of all. So now let's suppose that we wanted to find the z-score associated with a certain percentile. Okay? Then again, we want to identify the area from the left that matches the given percentile, locate the closest probability in the body of the table, and identify the corresponding z-score. Now, you do have to be a little bit careful with both of these from the standpoint of, like the percentile. You know, a question might ask about the 90th percentile, but if it's asking below the 90th percentile, that would be like to the left. If it's asking above the 90th percentile, the top 10% in other words, then that's to the right. You would still use the 0.9 from the table, but then you would have to subtract from 1 to get that top 10% instead of the bottom 90%. So you still got to pay attention to that left and right stuff. Alright, so let's look at some examples. It's another pretty short section. So find the z-score of the given area. So in this case here, let me go ahead and drop it down a little bit so we have we can see what's going on. So the area that's been shaded, notice that it's shaded to the left, 0.8749. That's associated with a z-score of 1.15. So in other words, what you're really saying is, you know, when you fall into this portion, that would be your z-score. So again, now how did I get that? Well, if I come look at the table, and again, since it's greater than 0.5, and we want 8749, well, that one's pretty close to 8749 right there. Let me move it over. 87493, that's pretty close to 8749. And you can see over to the side, 1.1, up above 0.05, so that's 1.15. So that's how we got that value. Over here, that shaded area, notice that the shaded area is less than 0.5, so we're going to end up with a negative z-score. We have 0.4052, so let me go find 0.4052, and so this is down towards the bottom of the page here, 0.40, 409, 401, so 4052. So that's pretty close to 4052, 0.40517. So 4 decimal places would be 0.4052, and that is negative 0.2, and then that is in the column. That was 0.04, and so that's how we got our negative 0.24. Now, as before, if we are not going to the left, we have to take that into account. So on this problem here, notice that the shaded area is to the right. The table only works to the left. So the first thing I'd have to do is subtract from 1 to have this portion, which is unshaded in this diagram, because that's what the table is going to see. So 1 minus 0.719 gives me 0.281. That's what's unshaded. That's the one that has a z-score of 1.15. So in this case, I would be saying, what is the area, if I was doing the previous section, what is the area above z-score of 1.15? Whereas in this case, what I'm really looking for is, here's the area, work my way backwards to get the appropriate z-score. And then, let's suppose I had a situation like this, where instead of being between two z-scores, I want to know what z-scores would bound the areas like you see in this picture. So first off, for the one on the left, okay, I can just look up 0.05, and if we looked up 0.05 real quick, so again, this is another one of those ones, 0.0505, that would be 0.495 if I was to 4 decimal places, and so right in between, 1.645. Now, if I looked up this one, notice that it's shaded to the right, so the first thing I'd have to do is subtract from 1. That would give me 95%. When I then look up 95% on the positive side of things, and here we have 0.9495, here we have 0.9505, so pretty much right in the middle between those two, 1.645. Please note the symmetry of the positive and negative sides. 0.05 on this side, 0.05 on that side. The one gave me a negative 1.645, the other one gave me a positive 1.645. Those would be the two z-scores associated or bounding those particular probability areas. Alright, now we're back to our Marine Corps example again, but this time, let me go ahead and put it up a little bit so we can see the whole problem. This time, instead of having the heights of 64 and 80, suppose we wanted to change that so only men that were in the shortest 3% of the distribution or the tallest 4% of the distribution. And obviously you could make the numbers anything you wanted. I just picked two different ones so that they weren't symmetrical in that way. What would the new height requirements be? So first off, 3%, that's an area of 0.03. Since it's the shortest 3%, that would be to the left. So when I look that up on the table, I get negative 1.88. 4%, the tallest 4%, well, that's to the right. In other words, up to the tallest person. So that one I have to subtract from 1, which gives me 0.96 to the left, and that gives me a z-score of 1.75. Now I plug them into that formula. X equals z times sigma plus mu, z-score times the standard deviation plus the mean. And note, this one comes out a little bit less than the mean because I had a negative z-score. Over here, this one comes out slightly above the mean because I had a positive z-score. So if all I wanted to do was exclude the shortest 3% and the tallest 4%, instead of having the numbers 64 and 80, I could have 63.7 and 73.9. All right, one last example. No, two to go. Okay, first off, test scores for the analytical writing section of a GRE. That's a graduate record exam. That's a test that you can take to get into graduate school after you get your bachelor's degree. In this case, notice it's a non-standard distribution, mean of 3.5, sigma of 0.87. So the question, let's start off with, what score can be the minimum score and still be in the top 10%? Okay. Now, here's the thing. Top 10%, it's kind of like up here, the tallest 4%. Top 10% means then that you're taller than the bottom 90%. And we need the bottom, or we need to the left, to use table 4. So, looking up 0.9 in the table, we get a z of 1.28. We run through it, and it turns out the score would be 4.61. So you'd have to have at least a 4.61 in order to be in the top 10%. Now, next, between what two values does the middle 80% lie? Okay, you got to think about this one just a little bit. All right, the middle 80%. So that means there's 10% on top and there's 10% below. That would be the other 20%. So we've already done the top 10%. We just did that one. But we'll need the bottom 10%. And of course, again, because of the symmetry, the top 10% had a z-score of 1.28. The bottom 10% had a z-score of negative 1.28. Plug them both in, and so it turns out any GRE score from 2.39 to 4.61 would be in the middle 80% of the distribution. All right, and then this last example here, what are z-scores for percentiles? Let's suppose that you wanted to know the z-score that matched the 40th percentile. And again, remember that when you see something like P40, basically that means, and this is true when you take a test that does your scores in percentiles, what it's telling you is your score is above, if it's a P40, 40% of all the other test takers. If you have a 75th percentile, you're above 75% of all the other test takers. So P40 is 0.4. Again, that's to the left. That gave us a z-score of negative 0.25. The 0.75, greater than halfway, that gave us a z-score of 0.67. And so really, this first three sections of Chapter 5 are using Table 4, looking up z-scores to find their areas, or looking up areas to find their z-scores. And then we use those to determine the probability, basically, of ending up in a shaded area. Because if you end up in the shaded area, for instance, if you think I'm randomly selecting somebody, what are the chances they're going to end up here versus they're going to end up here, or they're going to end up in the white part here versus the shaded part there. That's how we can use the standard normal distribution to find the probability of an event occurring. So that's it for section 5.3.